Dear students, I am Mr.Monikandan, Assistant Professor, Mechanical Engineering Department, Rohini College of Engineering and Technology, Palkulam, Kanyakumari District. I am happy to meet you on the video lecture series in the subject Thermal Engineering 1. The subject Thermal Engineering 1 is in the 4th semester Mechanical Engineering. This video lecture is lecture number 1 on Unit 1 of Thermal Engineering subject. We are going to discuss about the thermodynamic cycle, Autocycle. The topic to be covered in this lecture is Introduction to air standard cycles, the principle of Autocycle, and the air standard efficiency of Autocycle. And the learning outcome for this lecture, at the end of the lecture, students will be able to explain the working principle of petrol engine, apply the concept of Autocycle to solve problems. Both the COs are in Bloom's level 3. The Bloom's level are 1. Remembers, 2. Understand, 3. Apply, 4. Analyze, 5. Evaluate, and 6. Create. Recap. And the recap from the basics what we studied in the previous semester engineering programs, the subject like physics, mathematics, and engineering thermodynamics. In physics, you studied heat, specific heat, and thermodynamic laws, energy, etc. In mathematics, you studied arithmetic calculations. In engineering thermodynamics, you studied the basic concepts of thermal engineering, about heat engine, and the laws of thermodynamics, etc. These are all some of the topics which are all required for understanding the subject thermal engineering in a better way. Air standard cycles definition. A thermodynamic cycle is defined as a series of change of states such that the final state is identical with the initial state. If the working fluid is air, then the cycle is called air standard cycles. So this is what you studied earlier in engineering thermodynamics. Change of state is called thermodynamic process. Thermodynamic cycle is a sequence of thermodynamic process that involve transfer of heat and work. The sequence of process linked in such a way to produce power. Therefore, thermodynamic cycle is also called power cycles. So look at the PV diagram. 1, 2, 3 are states of the system. Change of state from 1 to 2 is adiabatic compression process, and 2 to 3 is isothermal expansion process, and 3 to 1 is isochoric heat extraction or constant volume heat extraction process. These three processes constitute a cycle so that the initial and final states are identical. Assumption to analyze air standard cycles. Some assumptions are made on air standard cycles to analyze it because the air standard cycles are theoretical or ideal cycle. The working substance is air and the cycle is closed cycle. The cycle is closed cycle means the mass remains constant, only energy crosses the boundary. There is no mass transfer, mass is constant one throughout the cycle. Open cycle means mass and energy crosses the boundary. The working substance is gas and the practical cycle is called gas power cycles. So far, the assumptions are 1. The working fluid behaves as perfect gas. So it obeys all the gas laws and perfect gas equation PV is equal to mRT. 2. The mass of the working fluid is constant. That's what the system is closed. We assume mass equal to constant. 3. All the processes that constitute the cycle are reversible, but in practical, all the processes are irreversible. 4. The heat supply and heat rejection are through constant temperature source and sink respectively, and there is no chemical reaction in the cycle. That is, the heat is supplied using a source and heat is rejected using a sink. And 5. The properties of working fluid remains constant throughout the cycle. The properties such as Cp, Cv and gamma are constant throughout the cycle. Sixth one, no heat loss between the system and surroundings. The system is completely insulated one, therefore the net heat transfer is equal to 0. Seventh one, the kinetic and potential energies of the working fluid are neglected. There is only one kind of energy transfer, the heat and work. There is no change in kinetic energy and potential energy. Autocycle was invented by a German scientist, Nicholas A. Otto, in the year 1876. Dear students, listen here. The cycle is assumed as a closed cycle. As per the assumptions, the cycle is assumed as a closed cycle. The working fluid is used over and over again in the engine. The working fluid undergoes different processes to perform the work and finally return to its original position. So students, look at the picture. An arrangement of piston and cylinder of an ideal engine is shown in figure. The cylinder wall and piston are made by insulated materials. There is no heat transfer during the process. Also, the piston is frictionless. There is no loss in work also. The cylinder head is a good thermal conductor and it is insulated by an insulated cap when it is needed. See the picture. A source or heat reservoir is used to supply the heat energy to the system. Similarly, a sink is used to absorb the heat energy from the system. Now, the cylinder is assumed to be contain air for a volume V1. The initial state of air is pressure P1 and volume V1 and temperature T1. The position of the piston before compression is known as BDC, that is bottom dead center. Now, the air inside the cylinder is compressed by means of external work up to the state 2. The cylinder walls are insulated, therefore there is no heat transfer during the compression. Since the process is called isentropic or adiabatic process, it is 1 to 2 indicated on the PV diagram. The position of piston after compression is TDC and the volume of cylinder is called clearance volume. The piston always reciprocating in between TDC and BDC. A single movement of piston from BDC to TDC or TDC to BDC is called stroke. So, at the end of the compression, the insulation cap is removed and heat source is brought to contact with the cylinder head. The quantity of heat Qs is supplied at constant volume. The pressure and temperature of the system is increased and it is indicated by the state 3. The process 2 to 3 is constant volume heat addition process. It is indicated on the PV diagram. When the system reaches state 3, the source is replaced by the insulation cap and the air allows to expand up to BDC. There is no heat transfer during the expansion of gas. Therefore, the expansion follows the law P to the gamma is equal to constant. That is adiabatic expansion, adiabatic process. The positive work is performed during this process. The process is 3 to 4 indicated on the PV diagram. When the piston reaches BDC, the insulation cap is replaced by the sink to absorb heat from the system to bring the system in the initial state. Heat is rejected at constant volume. The process is 4 to 1 is constant volume heat rejection indicated on the PV diagram. So now look at the PV diagram. The Autocycle consists of 4 thermodynamic processes. Process 1 to 2 is adiabatic compression and 2 to 3 is constant volume heat addition process and 3 to 4 is adiabatic expansion and 4 to 1 is constant volume heat rejection. The quantity of heat supplied to Qs is in process 2 to 3 and heat rejected is in process 4 to 1. At state 1, the properties are P1, V1 and T1. At state 2, the properties are P2, V2 and T2. And state 3, the properties are P3, V3 and T3. From process 2 to 3, the volume V2 is equal to V3. At state 4, the properties are pressure P4, volume V4 and temperature T4. So from process 4 to 1, there is constant volume process. The volume V4 is equal to V1. Changes in property of the system. As I explained earlier, the changes in property of the system are tabulated here. Process 1 to 2. 1 to 2 is isentropic compression or adiabatic compression. Piston moves from BDC to TDC. Pressure increases as the volume decreases. Temperature is also increases. Since there is no heat transfer during the process, the entropy remains constant. Process 2 to 3 is constant volume process. Heat energy is added to the system during this process. The volume remains constant, that is V2 is equal to V3. The pressure increases from P2 to P3 and temperature is also increases from T2 to T3. Entropy is also increases from S2 to S3. Process 3 to 4 is isentropic expansion. Positive work is performed during this process. The heat energy is converted into work. Therefore, temperature decreases from T3 to T4. Pressure decreases from P3 to P4 and volume increases from P3 to P4. The entropy remains constant since there is no heat transfer. The piston moves from BDC to TDC. Process 4 to 1 is constant volume heat rejection. Some amount of heat is rejected from the system to sink. The volume remains constant. That is, the position of piston is at BDC. The pressure decreases from P4 to P1 and temperature is also decreases from T4 to T1 and entropy is also decreases. Air standard efficiency of autocycle. Consider process 2 to 3. The process is constant volume heat addition. Quantity of heat energy supplied Qs is equal to, the process is constant volume process. Therefore, the formula is m into Cv into dt. dt is change in temperature. Therefore, Q is equal to m into Cv into T3 minus T2. Cv is the specific heat capacity at constant volume. M is the mass of air. Consider process 4 to 1. The process is constant volume heat rejection. The quantity of heat rejected Qr is equal to m into Cv into T4 minus T1 kilojoules. So already we studied in engineering thermodynamics. The net work output of a heat engine is equal to quantity of heat energy supplied minus quantity of heat energy rejected. The efficiency of autocycle is given by the ratio of net work output to heat energy supplied. So net work output is equal to Qs minus Qr divided by Qs, that is equal to 1 minus Qr by Qs. So we know Qr is equal to m into Cv into T4 minus T1 and Qs is equal to m into Cv into T3 minus T2. Simplify the equation, we can get the efficiency of autocycle equal to 1 minus T4 minus T1 divided by T3 minus T2. This is the efficiency of autocycle in terms of temperature. To simplify this equation, from the numerator term take T1 outside. From the denominator term, take T2 outside. So the equation becomes efficiency of autocycle is equal to 1 minus T1 by T2 into the numerator term is T4 divided by T1 minus 1 and denominator term is T3 divided by T2 minus 1. Take this as equation A. Consider process 1 to 2. The process is adiabatic compression. Applying the isentropic law, that is P to the power gamma is equal to constant. The relation between properties, temperature and volume, we can write T2 by T1 is equal to V1 by V2 to the power gamma minus 1. So T2 by T1 is equal to R compression ratio to the power gamma minus 1. Here R compression ratio is equal to V1 by V2, that is volume of air before compression divided by volume of air after compression. Consider process 3 to 4. The process is adiabatic expansion. So applying the law, so we can write T3 by T4 is equal to V4 by V3 to the power gamma minus 1. Here V4 is equal to V1 and V3 is equal to V2. Therefore we can write T3 by T4 is equal to compression ratio R to the power gamma minus 1. From equation 1 and 2, we can write T2 by T1 is equal to T3 by T4 or T4 by T1 is equal to T3 by T2. Take this as equation 3. Substituting equation 3 in A, we can get efficiency of Autocycle is equal to 1 minus T1 by T2. So we can write 1 minus 1 by T2 by T1. So T2 by T1 is equal to, we know, V1 by V2 to the power gamma minus 1. So V1 by V2 is compression ratio. So we can write the efficiency of Autocycle is equal to 1 minus 1 by compression ratio to the power gamma minus 1. From the above equation, it is clear that the efficiency of Autocycle depends upon the compression ratio only, and it increases with the increase in compression ratio. That is, the efficiency of Autocycle is directly proportional to compression ratio. Acknowledgement. I refer the following to prepare this video lecture. Thank you.